NASA has once again turned the Space Launch System into a disaster. After a successful wet dress rehearsal, a much more serious issue has now surfaced with SLS, serious enough that the rocket has to be rolled back to the vehicle assembly building for immediate repairs. That move officially pushes Artemis 2 to April. Just as frustration started settling in across the space community, Elon Musk stepped in and shifted the mood. He revealed the launch timeline for Starship Flight 12, and what felt like another setback for America's return to the moon quickly turned into renewed anticipation. So, what exactly went wrong with SLS this time? And when will Starship fly again? Let's break it all down in today's episode of Alpha Tech. On February 19, 2026, NASA carried out its second wet dress rehearsal for Artemis 2, and this time it was a genuine leap forward. After WDR-1 was plagued by the now infamous hydrogen leak at the ground-to-flight quick disconnect seals, the team went back to work. They replaced both the 8-inch and 4-inch seals, swapped out filters in the ground system, and even conducted an additional hydrogen integrity test to eliminate any lingering doubt. They weren't taking chances. And the result, it worked. The countdown began on the evening of February 18th. The rocket was powered up step by step, and more than 750,000 gallons of cryogenic propellant, liquid hydrogen and liquid oxygen, were loaded into the core stage and the ICPS upper stage right on schedule. But here's the part that really matters. Hydrogen leak rates dropped dramatically. Just 0.4% during fast fill, peaking at 1.6% during terminal count. That's significantly lower than Artemis 1 and, well, within safety limits. For a vehicle that has struggled with hydrogen in the past, that's a major technical milestone. The team also executed 2 full terminal countdown demonstrations. The first held at T33 seconds before recycling. The second cut off at T29 seconds. Exactly the kind of rehearsal you want before committing to launch day. Even the Orion closeout crew performed flawlessly. The hatch was secured, the white room cleared on time, everything clean and procedural. During the post-test conference, Lori Glaze, NASA's acting Deputy Associate Administrator for the Exploration Systems Development Mission. Directorate couldn't hide her excitement.
One thing I do want to say here today is that following that successful wet dress yesterday, we're now targeting March 6th as our earliest launch attempt.
That single sentence sent the entire space community into a frenzy. Because from that moment to launch day, there were barely more than 10 days left on the clock. For many, especially those who grew up watching the Apollo missions unfold in real time, this wasn't just another launch date. It was something deeply personal. The idea that humanity was finally heading back to the moon stirred up memories of black and white television, broadcast Saturn V thunder, and a moment when space exploration felt limitless. For that generation, Artemis 2 isn't just a mission. It's a revival of something they once believed defined an era. But the excitement didn't last long. Just hours after the press conference, NASA Administrator Jared Isaacman posted an unexpected update on X. He wrote, "After overnight data showed an interruption in helium flow in the SLS interim cryogenic propulsion stage, teams are troubleshooting and preparing for a likely rollback of Artemis 2 to the VAB at NASA Kennedy. This will almost assuredly impact the March launch window. Oh no, this is bad. And this time, it's more serious than the hydrogen leaks. With hydrogen leaks, NASA still had options. They could swap out seals, replace filters, troubleshoot directly on the pad during the wet dress rehearsal. It was frustrating, yes, but it was manageable without tearing everything apart. This is different. The issue now involves an interruption in helium flow inside the SLS interim cryogenic propulsion stage, or ICPS. And that changes everything. Because this isn't something you can simply patch up at the pad. It forces a full rollback to the vehicle assembly building for deeper inspection and repair. The ICPS is the upper stage of SLS for Artemis 2. It uses the RL-10B2 engine powered by liquid hydrogen and liquid oxygen. Its job is critical. After core stage separation, ICPS performs the trans-lunar injection burn the maneuver that sends Orion out of Earth orbit and onto a trajectory toward the moon. It also maintains stable pressure inside the cryogenic propellant tanks throughout flight. And that's where helium comes in. Helium is not just a supporting system. It is essential. It pressurizes the propellant tanks, pushing fuel into the engine without mechanical pumps. It also purges lines, valves, and engine components, preventing contamination, freezing, or unwanted chemical reactions. If helium cannot flow properly, propellant cannot reach the engine in a controlled way. And without that, the mission doesn't just get delayed, it fails. Here's what makes this especially troubling. During both wet dress rehearsal 1 and 2, the helium system appeared to function normally. Through fueling countdown operations and cryogenic procedures, everything looked nominal. The anomaly only revealed itself after WDR2 concluded on the evening of February 19th during a routine repressurization procedure designed to keep the vehicle in a safe configuration. At that point, helium suddenly stopped flowing through the vehicle, even though all previous phases had been clean. Right now, the rocket remains safe because ground-based purge systems are temporarily maintaining environmental control. But that is not a long-term solution. You cannot proceed toward launch with an unresolved helium flow anomaly inside the upper stage. NASA is now investigating several potential root causes. One possibility is an issue at the quick disconnect umbilical interface between ground systems and the rocket, similar in architecture to the previous hydrogen leak area. Another is a stuck or failed check valve onboard ICPS, which would be eerily reminiscent of the helium check valve issue that affected Artemis 1 back in 2022. A third possibility is a clogged filter somewhere between the ground system and the vehicle. Whatever the exact cause turns out to be, one fact is clear. Accessing and repairing helium hardware deep within ICPS requires the infrastructure of the vehicle assembly building. That means removing platforms, opening internal access points, and working in a controlled, fully supported environment. The earliest target to roll both SLS and Orion back from the pad to the VAB, according to NASA's latest update, is the 25th. The move has been delayed by 1 day due to weather conditions. Once inside, the VAB teams will begin tear-down operations, inspect the hardware, replace components if necessary, and then retest the entire helium system before rolling the vehicle back out to the pad again. But who's to say that rolling the vehicle back and forth won't accidentally bring back that infamous hydrogen leak again? If that happens, April could be gone too. And then, we're not talking about a spring launch anymore. We're talking about a launch at the end of the year. Which year, I'm not entirely sure. But hey, don't be too discouraged. After all the workforce supporting Artemis, 2 will continue getting paid through every delay, right? And even if NASA had launched on time, would anything fundamentally change? SLS and Orion aren't revenue-generating vehicles. They're not launching commercial satellites. They're not ferrying astronauts to the ISS on a steady cadence. They don't create a recurring stream of income. Their purpose is strategic. They were built and sustained to secure America's position in the lunar race, particularly against China, a race the United States already won once in the last century. So maybe watching another vehicle fly is in its own way more exciting. Take Starship. It's not just designed for the moon. It's aimed at Mars. It represents something broader, something commercially ambitious and interplanetary. Almost immediately after Isaacman confirmed the Artemis 2 delay, Elon Musk posted a short but electrifying message: Starship flies again next month. Just 5 words. Yet it drew more than 400,000 likes. That alone tells you how massive and engaged the Starship community has become. Some critics even suggested Musk was trying to redirect the narrative, easing pressure on Isaacman by shifting public attention. But speculation aside, if Musk is correct, then the next Starship flight could happen in just 2 to 3 weeks. But doesn't that also feel like a subtle jab at NASA? On one side, you have a privately developed vehicle with a clear long-term vision, an aggressive roadmap, and a business model that aims to generate serious revenue. And it's setting launch targets with confidence. On the other side, you have a government-funded system with no commercial revenue stream, no routine crew rotation role. It exists primarily as a strategic, politically driven program, and despite years of development and tens of billions of dollars invested, it continues to slip. And yet, despite all of that, SpaceX still gets criticized for being behind schedule on Starship HLS. What many people overlook is the sheer scale of what SpaceX is attempting on the next Starship flight. Take Super Heavy Booster 19. This isn't just another booster. It's the first Block 3 Super Heavy, designed for a full return-to-launch site profile. That means after stage separation, instead of heading for a downrange splashdown, the booster performs a boost-back burn at roughly 70 kilometers altitude flips. Using its cold gas thrusters, reorients and flies all the way back to Starbase to be caught mid-air by the Mechazilla arms on the launch tower. That capability isn't theoretical anymore. In February 2026, the FAA approved the final tiered environmental assessment, clearing new RTLS mission profiles. The approval included updated airspace closures and provisions for Starship Boca Chica landings, effectively paving the way for booster returns and tower catches at the pad without significant environmental impact. This is a bold move. Block 3 hardware introduces the new Raptor 3 engines, and for the first time, all 33 engines are expected to operate together in a fully integrated ascent profile. Attempting an RTLS catch at the launch site with an upgraded propulsion system raises the stakes significantly. It's ambitious, it's risky, and it's exactly the kind of high-data flight SpaceX tends to pursue. But there's logic behind it. Accelerating booster reusability is critical if SpaceX wants to support the tanker launch cadence required for Artemis 3. Rapid turnaround, reliable RTLS, and consistent tower catches dramatically reduce operational costs and increase launch tempo. So, are you excited to see it happen? If you're ready to see Starship push the limits again, drop a comment, go Starship. There's another reason Flight 12 is so exciting to watch. It's not just about the big milestones, it's about the small details. Over the past few days, SpaceX has been repeatedly testing the water deluge system at the pad, and the sheer volume of water blasting upward is incredible. To be honest, even 33 Raptor 3 engines wouldn't be enough to overpower the force of that spray during ignition. The water shoots so high, it completely obscures the booster mock-up at times, almost like the launch pad itself is pushing back against the rocket. It's a vivid reminder of how much engineering goes into protecting the infrastructure, not just the vehicle. Acoustic suppression, thermal protection, structural damping, all of it has to work perfectly when that full thrust column hits the pad. Right now, it's not just Elon Musk thinking long-term. NASA is looking at the same future. Both sides are aiming for a sustainable lunar base, often called Moonbase Alpha. And this isn't about planting flags, it's about building infrastructure. We're talking about a fission surface power system, a compact nuclear reactor that can deliver steady power through the brutal 2-week lunar night when solar simply isn't enough. We're talking about mass drivers, electromagnetic launch systems that could fire AI satellites or refined lunar materials into orbit at incredibly low cost, taking advantage of the moon's low gravity and vacuum. That's how you build a real space economy. ISRU, manufacturing on the surface, a permanent presence, and eventually a launch point for Mars. But none of this matters unless Starship HLS proves it can safely land on the moon and bring astronauts back to lunar orbit. That's the key step. Without it, there's no reusable high-cadence lunar system. Starship has always been pitched as a high-performance, low-cost vehicle built around reusability. Musk has suggested a standard Starship flight could eventually drop below $10 million. An HLS mission could run closer to $100 million, mainly because that version doesn't return to Earth. But that's not a deal-breaker. HLS can stay in lunar space and potentially become part of the base itself. Super Heavy still returns to the launch site and flies again. The real problem is this. Even if Starship HLS successfully lands astronauts on the lunar surface and brings them safely back to lunar orbit, the round trip between Earth and the moon still depends entirely on NASA's legacy architecture, Space Launch System, and Orion. And that's the bottleneck. These systems are often criticized as outdated because they inherit design philosophy and hardware lineage from Apollo and Constellation-era technology. They are not reusable. Their production chains are complex, and the cost reflects that reality. Each SLS launch is estimated at roughly $2 to $4 billion, not including Orion. The technical fragility only adds to the problem. On February 19th, NASA completed a second wet dress rehearsal for Artemis 2, a full propellant loading test. On paper, that was progress. But shortly afterward, engineers detected a serious helium flow disruption in the interim cryogenic propulsion stage. The issue forced a rollback of the entire stack to the vehicle assembly building for inspection and repair eliminating the March 2026 launch window and pushing the mission at least into April, possibly later. This pattern is what turns Artemis into a slow, extremely expensive program vulnerable to recurring technical delays. It stands in direct contrast to the Starship philosophy: rapid reuse, low marginal cost per flight, and high launch cadence. Now consider the long-term vision. Building something like Moonbase Alpha won't take 2 astronauts. It could require 20 or more over multiple missions. Under the current SLS Orion model, that could translate into $20 to $40 billion, largely funded by taxpayers. So, the question becomes obvious. Why not remove SLS and Orion from the lunar transport chain altogether? If Earth-to-Moon transport were handled entirely by Starship architecture, mission cost could drop by an order of magnitude. Instead of multi-billion-dollar launches, the primary expenses would be propellant for Super Heavy, and production of a Starship HLS variant potentially under $100 million per vehicle. Add crew salaries and operations, and you are no longer talking about billion-dollar missions. On paper, it makes economic sense. And this isn't just speculation. In late October 2025, after analyzing the data from Starship Flight 11, SpaceX appeared to uncover something significant. Whatever they saw in that dataset clearly strengthened their confidence, confident enough that they formally proposed a simplified mission architecture to NASA for Artemis 3 and the missions that follow. They haven't made the full details public, but based on what we know, the simplification likely points in one of 2 directions. Option 1, remove SLS and Orion entirely. In other words, transport astronauts from Earth to the Moon and back using only Starship-based hardware. Option 2, reduce the number of orbital refueling launches required to prepare HLS for lunar descent, streamlining the campaign and lowering operational complexity. Most analysts suspect the first option is the more radical, and therefore the more intriguing. Because if SpaceX is truly proposing to cut SLS and Orion out of the loop, that would fundamentally reshape the Artemis architecture. So, if that's the case, how would they actually pull it off? The sequence could start in a surprisingly straightforward way. NASA would still use Orion, fully assembled just like today. That means the crew capsule, the European service module, providing power, propulsion, oxygen, and water, and the launch abort system, the safety layer NASA insists on after the hard lessons of Challenger and Columbia. Altogether, that stack weighs somewhere in the 35 to 50-ton range. Here's the twist. Instead of sitting on top of SLS, Orion would ride inside Starship's payload bay. Starship would launch from LC-39A at Kennedy Space Center, or possibly from a new SpaceX pad. Raptor engines would push the entire stack to low Earth orbit roughly 200 kilometers up. Once stable in orbit, Starship would gently deploy Orion. Because this version of Starship would fly expendable, it could burn all remaining propellant to maximize delta V and push Orion as far as possible toward the Moon before separation. From there, Orion takes over. Using the main engine on the European service module, and possibly an additional kick stage if required, Orion would perform the trans-lunar injection burn. 3 to 4 days later, it reaches lunar space. No complex on-orbit assembly. No long chain of risky tanker refueling launches just to send crew beyond Earth orbit. Waiting near the Moon would be Starship HLS, already fueled and staged in NRHO, or low lunar orbit. The 4 astronauts transfer from Orion to HLS, descend toward the lunar south pole, perhaps near Shackleton Crater or other high-value scientific sites. They conduct EVAs, deploy instruments, collect samples, stay for several days, or even a couple of weeks. When the surface mission is complete, HLS lifts off, returns to lunar orbit, and docks again with Orion. The crew transfers back. HLS either remains in lunar space as infrastructure or follows whatever reuse plan SpaceX ultimately adopts. Orion then performs the return burn, accelerates toward Earth, re-enters at high velocity using its proven heat shield, and splashes down in the ocean. No SLS. That single change could eliminate $2 to $3 billion per mission, avoid the recurring hydrogen leak delays, and dramatically increase launch flexibility. At the same time, it would validate Starship as the true heavy lifter in the architecture. So, what do you think? Does it look cheaper and simpler? If you're still not convinced, then let's take a look at a second approach, one that doesn't need SLS and doesn't need Orion either. The concept leans fully into Starship as a unified, fully reusable system refined through recent test flights where orbital refueling has started to show real progress. The sequence begins in low Earth orbit, but instead of launching a single HLS vehicle, SpaceX would launch 2 Starships. First comes Starship HLS, the lunar-optimized lander version equipped with reinforced landing legs and a habitat capable of supporting astronauts on the surface for days or even weeks. It would launch from Starbase or LC-39A reach LEO and dock with a propellant depot for orbital refueling. Once fully fueled, HLS would perform a burn toward lunar orbit, staging itself either in near rectilinear halo orbit or low lunar orbit depending on mission design and energy margins and weight there for the crew. Next comes the crew. 4 astronauts, potentially more in future missions, would launch aboard a second Starship configured for crew transport. Unlike the pure HLS variant, this vehicle would be equipped with a heat shield for Earth re-entry. It would launch to LEO dock with the depot refuel in orbit, and once topped off, execute the trans-lunar injection burn. 3 to 5 days later, it reaches lunar orbit. Compared to Orion, the crew would have significantly more volume and internal space during transit. No intermediate spacecraft, no separate capsule transfer. The crewed Starship would dock directly with the waiting HLS. From there, the mission shifts to the surface phase. The astronauts transfer into HLS and perform a propulsive descent to the lunar south pole. On the surface, they could deploy scientific instruments, test ISRU, hardware, operate rovers designed to explore or even mine water ice and conduct extended EVAs. Surface stays could last several days, possibly 1 to 2 weeks, even longer, as early base modules are added. Compared to Apollo, this represents a major leap in endurance supported by advanced life support and the ability to deliver massive cargo capacity. When the surface mission is complete, HLS lifts off using its Raptor engines, taking advantage of lunar gravity at 1/6 of Earth's. No separate ascent stage required. It returns to lunar orbit and docks once again. For the return to Earth, the crew transfers back into the heat shield-equipped Starship. That vehicle performs trans-Earth injection and heads home. Upon arrival, it re-enters using its ceramic heat shield and aerodynamic flaps, followed by a propulsive landing either at sea or on land. No Orion required. Starship was designed from the beginning for high-energy re-entry and has undergone multiple test campaigns since 2024 to validate that capability. Economically, the difference is dramatic. A fully reusable Starship-based mission could potentially cost a few $100 million compared to roughly $4 billion for a single SLS Orion flight. Just as important, cadence increases. Instead of waiting years between missions, launches could happen annually or even more frequently. It's a model aligned far more closely with Elon Musk's long-term vision, high frequency, lower cost, and a sustained human presence beyond Earth. So, what do you think about this second approach? Compared to the first one, which direction makes more sense? Let me know in the comments. There's also a third option, and honestly, it might be the simplest and most practical of them all. Instead of using SLS and Orion, NASA could use Crew Dragon launched on Falcon Heavy as the taxi to low Earth orbit. The logic is straightforward. First, SpaceX launches Starship HLS and positions it in lunar orbit fully fueled and ready. Only after everything checks out does the crew launch aboard Crew Dragon, a system that has already flown dozens of operational missions to the ISS and proven itself highly reliable. The astronauts reach low Earth orbit, transfer to a waiting Starship configured for deep space, and then head to the moon. They dock with HLS, descend to the surface, complete their mission, return to orbit, and eventually make their way back to Earth. In simple terms, you replace a multi-billion-dollar launch system with one that costs tens of millions. This hybrid approach maximizes what already works. Falcon Heavy and Crew Dragon handle crew transport to orbit at relatively low cost. Starship handles the heavy lifting deep space transit and lunar landing. The result? No SLS, no Orion, dramatically lower cost, faster cadence, and arguably higher operational flexibility. NASA is now facing one of the most critical moments of the Artemis program. Artemis II, the first crewed mission to fly around the moon in more than half a century. Under the current schedule, the SLS rocket and the Orion spacecraft are already stacked on Launch Pad 39B at Kennedy Space Center in Florida, with teams preparing for the wet dress rehearsal, the crucial full-scale fueling test. But just as excitement began to build, a wave of controversy erupted centered largely on Orion's AVCoat heat shield, the protective layer responsible for surviving temperatures of several thousand degrees as the spacecraft slams back into Earth's atmosphere at roughly 11 kilometers per second. Two of the most prominent voices raising concerns are Charlie Camarda, a former space shuttle astronaut and heat shield specialist, and Daniel Raske, a retired NASA thermal systems engineer with more than 30 years of experience. Raske is also the co-inventor of Pica phenolic impregnated carbon ablator, an ultralight, highly heat-resistant material that later became the foundation for SpaceX's Pica X heat shield on Crew Dragon. Both men have publicly expressed serious concerns on television, arguing that Orion's current heat shield, still based on AVCoat technology dating back to the Apollo era of the 1960s, carries unacceptably high risk. Camarda went so far as to call flying Artemis 2 with an essentially unchanged design, crazy, emphasizing that debris shedding during Artemis 1 suggests the system is already operating near a potential failure threshold. Raske was even more blunt, rating the heat shield an outright F, the lowest possible grade, and stating plainly that humans should not be flown on a system like this. Both experts suggested that robotic missions would be the wiser choice, pointing out that the United States has already won the moon race once and does not need to rush at the cost of unnecessary risk. They also invoked the Challenger and Columbia disasters as sobering reminders that avoidable risks can lead to tragedy. NASA, however, has not ignored these criticisms. The agency spent 18 months conducting an in-depth investigation and ultimately identified the root cause as trapped gases within the AVCoat material, which were not venting quickly enough during the ablative process. Rather than replacing the entire heat shield, a move that would be extremely costly and cause major delays, especially since the Artemis 2 heat shield had already been installed, before Artemis 1 NASA chose a different solution. The key change lies in the return trajectory. Specifically, NASA has shifted from a skip entry profile, where the spacecraft briefly skips off the atmosphere before re-entering, to a more direct entry path. This reduces the duration of peak heating and lowers overall stress on the heat shield. Program leaders such as Howard Hugh Orion, program manager, along with newly appointed NASA Administrator Jared Isaacman, have stated that every aspect of the issue was thoroughly reviewed. External experts and critical voices were invited into the discussion. Isaacman emphasized that he requested detailed reports early on, encouraged open and transparent debate, and that the results ultimately reinforced confidence in the technical decision. NASA now maintains that with these changes, the astronauts will be safe. The heat shield may still experience surface damage, but not at a level that threatens crew survival. That said, heat shield risk only becomes critical during re-entry on the very last day of the mission. And this time, Artemis 2 is planned to last 10 days, which means for the other 9 days, the 4 astronauts will be facing challenges that may be even more serious than the heat shield itself. Before the crew ever steps inside the Orion capsule, the SLS rocket must be fully loaded with cryogenic propellants, liquid hydrogen and liquid oxygen. This is an inherently dangerous process. These propellants are extremely volatile, highly flammable, and prone to leaks. If something goes wrong, unstable tank pressure, a faulty valve, or an undetected leak, the entire rocket can effectively turn into a massive bomb, threatening not only the crew, but also the ground teams working nearby. NASA reduces this risk by taking a far more conservative approach than SpaceX. Instead of fueling with the crew already on board, NASA loads the propellants first, then brings the astronauts in, afterward minimizing their exposure to the most hazardous phase. On top of that, teams run extensive system checks, emergency simulations, and use data from Artemis 1 to refine every step of the process, ensuring everything is as stable as possible before the countdown even begins. Then comes the moment of truth. At T04, RS, 25 engines and 2 massive solid rocket boosters ignite, generating about 8.8 million pounds of thrust and hurling the vehicle off the pad with brutal acceleration. This is the single most dangerous moment of the entire mission. If an engine fails, an SRB detonates, or the rocket loses control, the outcome could be instantly fatal. To counter that risk, NASA equipped Orion with a Launch Abort System, or LAS, a small but incredibly powerful rocket tower mounted on top of the capsule. If disaster strikes, the LAS can yank Orion away from a failing rocket in a fraction of a second, subjecting the crew to accelerations of roughly 15 to 20 Gs, before deploying parachutes for a splashdown in the Atlantic Ocean. And yes, those G-forces are extreme. The astronauts are positioned lying on their backs in what's known as a supine eyeballs in orientation. This is the optimal posture for surviving high acceleration, allowing the force to be distributed from the chest through the back, while reducing dangerous blood pooling in the legs or excessive pressure in the head. Even so, when the LAS fires producing around 15 to 17 G for roughly 2 to 3 seconds, the stress on the human body is immense. Astronauts describe it as feeling like an elephant sitting on your chest. Breathing becomes nearly impossible. You can't move your arms or legs. You can't even speak. Blood is forced hard toward the back and head, creating intense pressure on the eyes, ears, and internal organs, resulting in severe full-body pain. In poorly restrained scenarios, there is even a risk of rib fractures or spinal injury. However, NASA designed the system, so these extreme forces last only for a very brief window, under 3 seconds, just long enough to get the crew clear of an explosion. Combined with specially engineered seats that support the entire body and extensive astronaut training, this level of G-load is not considered lethal or likely to cause permanent injury in healthy crew members. In short, without the launch abort system, the crew would be in far greater danger. But that still isn't everything. About 2 minutes into flight, the solid rocket boosters separate. Then around the 8-minute mark, the SLS core stage shuts down, leaving Orion attached to the interim cryogenic propulsion stage, or ICPS, in an initial parking orbit around Earth. This phase lasts only a few minutes, but it carries real risk. A faulty separation, if the core stage doesn't detach cleanly, could throw the spacecraft off its intended trajectory or even damage its structure. NASA mitigates this using automated sensors and highly precise guidance software refined using lessons from Artemis 1. During that uncrewed mission, thermal effects from engine plumes interfered with sensors and caused attitude data errors. Those issues have since been corrected. On top of that, the Artemis 2 crew has logged thousands of hours in simulators, training to take manual control if necessary, ensuring the vehicle remains stable before entering proximity operations during the first 24 hours. In this phase, the ICPS performs a burn to raise Orion into a higher Earth orbit. Orion then separates and the crew manually flies around the now expended upper stage, checking cameras, sensors, and flight controls. The risks here include collision or software faults, leading to loss of control, especially critical, given this is the first time Orion will be flown by humans in real space conditions. To reduce those risks, NASA integrated automated collision avoidance systems and extensive crew training, while software was optimized using Artemis 1 data. This experience is also crucial preparation for future missions involving docking with Gateway or even Starship. Next comes the trans-lunar injection, burn the maneuver that pushes Orion out of Earth's gravity well and sends it on a 4-day inertial cruise toward the moon along a free return trajectory. This inertial flight phase is the longest stretch without major engine burns, but it introduces a different kind of danger space radiation. Galactic cosmic rays and solar particle storms can cause acute radiation sickness and damage onboard electronics. The crew will be operating outside Earth's protective magnetosphere, and solar cycle 25 is near its peak, further increasing the risk. NASA counters this by designating a radiation shelter in the center of the cabin, using the heat shield beneath the floor as part of the shielding. Astronauts are also trained to stack water containers, food supplies, and clothing around themselves to create an improvised barrier capable of reducing radiation exposure by up to 50%. In addition, the crew will wear Astro radiation protection vests, refined using Artemis 1 data from the Helga and Zohar radiation mannequins. Real-time space weather monitoring allows mission control to issue rapid alerts if solar activity spikes. Throughout this period, the crew continuously checks spacecraft systems and rehearses emergency procedures, turning isolation in deep space into an opportunity to sharpen readiness. Around day 6 of the mission, Orion reaches its closest approach to the moon, passing at a distance of roughly 6,500 kilometers. The spacecraft swings behind the far side and uses a gravity assist to bend its trajectory back toward Earth. This is the most dramatic moment of the entire flight. For about 30 to 45 minutes, as Orion passes behind the moon, all communications are completely cut off. The moon blocks every signal. The crew is truly alone. If something goes wrong during this window, there is no help from Earth. They have to handle it themselves. Additional risks come from the moon's uneven gravitational field, which can introduce navigation disturbances, as well as the possibility of minor impacts from micrometeoroids. NASA mitigates these dangers by designing Orion to be highly autonomous with multiple layers of redundant software. The crew is also trained to observe the lunar surface directly through the windows, collecting visual and geological data that will support future missions. Meanwhile, the Deep Space Network has been upgraded following communication dropouts experienced during Artemis 1. Antenna allocation has been optimized, and new software has been deployed to minimize interruptions before and after the blackout period. The gravity assist allows Orion to turn back toward Earth without a major engine burn, and the free return trajectory ensures that even if something goes wrong, the spacecraft will naturally fall back toward home safely. Recently, Amazon, Jeff Bezos' empire, made a move that caught almost everyone off guard. The company quietly turned to SpaceX, Elon Musk's SpaceX, asking for help to save a project worth tens of billions of dollars. That project is Project Kuiper, now increasingly referred to as Amazon LEO. Amazon's ambitious broadband satellite constellation, built with one clear goal to go head-to-head with Starlink and beat Elon Musk at his own game. But this story isn't just about rockets and satellites. It's a long-running drama fueled by pride, personal rivalry, and the unforgiving reality of the space industry. Here's how it all unfolded. Amazon's Project Kuiper was approved to deploy a massive constellation of 3,236 satellites. The FCC was on board and granted Amazon the license, but with a very strict condition attached. Amazon must deploy at least half of the constellation, around 1,618 satellites, and have them operational by July 30th, 2026. Miss that deadline, and Amazon risks losing the license entirely, potentially forcing the program back to square one or into a legal nightmare. It's precisely because of that brutal deadline that Amazon went on a rocket buying spree all the way back in 2022. They locked in launch contracts with Blue Origin for New Glenn, ULA for Vulcan Centaur, and Ariane Space for Ariane, 6 more than 80 launches in total, potentially over 100, if all options are exercised. And here's the part that raised eyebrows across the industry. SpaceX, by far the most reliable launch provider in the world at the time, with Falcon 9 flying hundreds of missions, unmatched reusability, lower costs, and an aggressive launch cadence, was completely shut out. Not a single contract. The reason was obvious. Jeff Bezos had no interest in relying on Elon Musk, a rival he had openly mocked in the past, even dismissing Musk's Mars ambitions as unrealistic and science fiction. But that decision came at a cost. In 2023, Amazon's leadership, including Bezos himself, was hit with a lawsuit from the Cleveland Bakers and Teamsters Pension Fund. The accusation was blunt. Amazon had failed to act in the best interest of shareholders by deliberately excluding SpaceX from the bidding process, driving up costs and increasing execution risk for Project Kuiper. Eventually, reality caught up. Amazon reluctantly signed launch contracts with SpaceX, starting with 3 Falcon 9 missions scheduled for 2025. But by then, the damage was already done. Today, with only 180 satellites in orbit, Amazon still needs to launch more than 1,400 satellites before the FCC deadline. And with the clock ticking down to mere months, the margin for error is essentially gone. Things became even more serious as New Glenn slipped further and further behind schedule. Blue Origin is still struggling just to prepare for its third flight, a mission meant to prove that the rocket can actually be reused. Until that happens, no one can say when New Glenn will be ready to carry Kuiper satellites. At the same time, Amazon's other launch bets haven't helped much either. ULA's Vulcan Centaur has faced major delays of its own, and Ariane 6 has also fallen well behind schedule. One by one, the rockets Amazon was counting on failed to show up on time, effectively freezing Kuiper's launch plan. Facing that reality, Amazon made a desperate move. On January 30th, the company formally asked the FCC for a 24-month deadline extension, pushing the requirement to deploy half of the constellation out to 2028. The justification? A shortage of available launch vehicles and factors supposedly beyond Amazon's control. But the FCC may not be easily convinced. And that's exactly why Amazon quietly went back to SpaceX, signing an additional 10 Falcon 9 launches on top of the deals already in place. The message to regulators was clear. We're still fighting. We still have a path forward. Ironically, that move did the opposite in the court of public opinion. Instead of inspiring confidence, it triggered laughter across the space community. Because by buying even more Falcon 9 flights, Amazon was effectively admitting the unthinkable, that New Glenn, the rocket Bezos was supposed to rely on, when it mattered most, still isn't ready, still isn't reliable, and still can't be trusted under pressure. The reliability Amazon desperately needs has shifted almost entirely to SpaceX. Elon Musk hasn't said a word about the situation, but it's not hard to imagine him quietly enjoying the irony. And in the end, SpaceX doesn't care what your satellites are for or whose constellation you're building. If you buy the launch service, pay the bill, and show up on time, Falcon 9 flies. As of now, Amazon has officially committed to a total of 13 Falcon 9 missions dedicated to the Amazon LEO program. 3 of those flights were completed smoothly throughout 2025 in July, August, and October, with each mission carrying exactly 24 satellites to orbit. That puts 72 Kuiper satellites delivered by Falcon 9 alone. Now, if we assume the 10 newly signed Falcon 9 launches all take place in 2026, and each maintains the same payload of 24 satellites, that adds another 240 satellites to the constellation. On paper, that sounds impressive, but measured against the FCC's hard requirement, it's actually alarming. To keep its license, Amazon must deploy and operate at least half of the constellation. 240 satellites doesn't even reach a quarter of that threshold. And even after factoring in launches, Amazon is still hoping to fly on other rockets. Internal projections reportedly point to only around 700 satellites in orbit by the deadline. That's a dangerous place to be. Here's the interesting part, though. Falcon 9 could still be the lifeline if Amazon decides to go all in. SpaceX demonstrated its launch cadence in 2025 with a record 165 Falcon 9 flights averaging 13 to 14 launches per month, with peak months like May and November hitting 16 launches. In theory, Falcon 9 can support 10 to 15 launches per month, if given high priority thanks to boosters flying dozens of times to primary launch sites at Cape Canaveral and Vandenberg, and extremely fast turnaround operations. Of course, SpaceX can't dedicate its entire manifest to Amazon. Starlink NASA missions, national security launches, and other commercial customers all come first. But if progress remains sluggish after the 10 contracted flights are completed, Amazon may have little choice but to return to the negotiating table, potentially buying another 20 Falcon 9 launches between 2026 and 2027, or even more, if the rockets originally assigned to Kuiper fail to materialize. In the end, this is a lesson for everyone in the industry. Never underestimate anyone in this business. The company you dismissed today might be the one that saves your program when everything is on the line. Now, let's move on to another development. Just days ago, on February 2nd, 2026, U.S. Secretary of Defense Pete Hegseth paid an official visit to Blue Origin's rocket factory at Merritt Island, Florida, right next to Cape Canaveral. This marked the first time a Secretary of Defense under Trump's second administration has personally visited Blue Origin. The visit was part of Hegseth's month-long Arsenal of Freedom tour, aimed at inspecting major defense contractors, pushing for faster production, and reasserting American strength in space. During the visit, Hegseth met directly with Jeff Bezos, toured the massive 750,000 square foot manufacturing facility, where New Glenn and components for the Blue Moon lander are being assembled, and then addressed hundreds of employees in a fiery, almost campaign-style speech. "We will unleash American space dominance." Space is the ultimate high ground. What makes this visit noteworthy is that many observers had assumed the Pentagon would keep its distance from Blue Origin for quite some time. The reason is simple delays. New Glenn, the heavy-lift rocket expected to compete in the National Security Space Launch Program, took years to reach its first flight in 2025. While it has since completed several successful missions, its launch cadence remains low and far from stable enough to handle large volumes of sensitive national security payloads. Blue Origin was famously shut out of NSSL Phase 2 back in 2020. It was only brought back during Phase 3 Lane 2 in 2025, with the potential to fly up to 7 missions between 2027 and 2032. Even so, it has not yet received a single actual launch assignment, largely because certification for national security payloads is still ongoing. For years, analysts and space policy watchers speculated that Pentagon leadership, particularly under the Biden administration, was unwilling to reward a company perceived as slow-moving and lacking cadence, especially when compared to SpaceX or even ULA with Vulcan. The absence of high-profile visits was widely interpreted as a quiet signal of frustration, with priority given to providers that had already proven speed reliability and consistency on missions like GPS, intelligence satellites, and Artemis support. But Hegseth's visit tells a very different story. He didn't just stop by for a courtesy tour. He used Blue Origin's factory floor as a platform to openly criticize the outdated defense procurement system, legacy contractors plagued by delays, cost overruns, and a lack of innovation. He made it clear that the Trump administration intends to prioritize agile commercial companies capable of rapid, large-scale production. And he explicitly framed Blue Origin as one of the future winners. Hegseth praised the facility, saying that, based on what he saw, Blue Origin is positioned to win big in upcoming government contracts. The timing was also notable. The visit coincided with Blue Moon Mark I Endurance arriving in Houston for thermal vacuum testing at NASA's Johnson Space Center as part of its preparation for Artemis and potentially future military applications. While New Glenn is still in the certification phase, the message from Hegseth was unmistakable under his leadership. The Pentagon is more open to new entrants like Blue Origin, provided they can demonstrate speed and scale the very qualities he is now pushing across the entire defense industrial base. This development flips the old narrative on its head. Many assumed Blue Origin had been sidelined because of its delays. Instead, this visit suggests the new administration is actively courting the company as part of a broader strategy, diversifying launch providers, encouraging competition among commercial players, and countering China's growing presence in space. It's no coincidence that phrases like American space dominance and peace through strength were delivered from Jeff Bezos' factory floor. It looks like a deliberate attempt to balance an already dominant SpaceX with a Blue Origin that's still chasing but strategically valuable. That said, reality remains unforgiving. Blue Origin still needs to dramatically increase its launch cadence if it wants to become a serious player in military space contracts. This visit may be a powerful vote of confidence, but it's also a reminder that in the Pentagon's eyes, speed is king. So, what do you think? Is this a sign that Blue Origin is truly regaining momentum, or is it simply a political gesture? Drop your thoughts in the comments below. In the past, SpaceX typically needed about 3 to 4 months to manufacture all the major components for one Starship and one Super Heavy. If you include final assembly, the whole process could stretch to around 6 months. But SpaceX builds multiple vehicles at the same time. So in 2025 alone, they managed to produce roughly 4 Super Heavy boosters from B-15 to B-18 and 5 Starships from S-34 to S-38. For many companies, Blue Origin, for example, that would already be considered a fast production pace. Last year, Blue Origin produced just 2 New Glenn boosters, despite having a massive rocket factory covering 750,000 square feet. Ironically, Starship follows a more complex and less streamlined process, yet still delivers higher output. That's mainly because SpaceX manufactures individual sections inside the Starfactory, then moves them into nearby Megabays for stacking and integration. This process actually takes less time than shipping Raptor engines from SpaceX's McGregor facility, which is over 400 miles away from Starbase. And that's exactly why Elon Musk decided to build 2 enormous new buildings called Gigabays, one massive structure at Starbase, replacing the old high bay, and another at the Roberts Road facilities, located inside Kennedy Space Center. The goal is to optimize the entire production process and push output even further. As Musk recently said, once the Gigabays are fully operational at peak capacity, SpaceX could potentially build up to 10,000 ships per year. That's about 27 vehicles a day. Sounds crazy, right? Because it almost feels like he wants to bring automotive-style mass production into the aerospace industry. And what makes it even more insane is that this isn't a few-ton car. It's a 300-ton, 2-stage, full-stack vehicle, standing 124.4 meters tall in the current version 3. And in the future, it'll be even bigger. According to Musk, version 4 could reach around 142 meters when fully stacked. So, is the 10,000 ship number realistic? In theory, yes, but that's clearly a long-term vision. In the nearer window, roughly between 2027 and 2030, if the Gigabays come online on schedule, a more realistic output would be around 1,000 Starships per year. And that makes sense when you look at the Gigabay configuration itself. Each Gigabay is essentially a fully integrated facility, combining the roles of today's Starfactory and Megabays into a closed-loop production system. The building stands 380 feet tall, about a 40-story building, offering up to 815,000 square feet of floor space and roughly 46.5 million cubic feet of interior processing volume. Inside, it's equipped with 24 dedicated work cells designed for integration and refurbishment of both Super Heavy boosters and Starship vehicles. That's 19 more work cells than the old Megabays setup. Now, imagine that scale, and then double it, because SpaceX is building 2 gigabays, not just one. And the construction progress so far looks solid, with both facilities expected to be operational by the end of 2027, ready for full-scale mass production. That timeline also lines up neatly with another bold statement Elon Musk recently posted on X, where he said, in about 3 years or so, Starship will launch more than once per hour. That number is almost impossible, because even with Falcon 9, where SpaceX just set a new turnaround time record at SLC 40, the fastest reuse cycle is still around 45 hours. But it may still happen. If SpaceX can really produce thousands of Starships per year, then it has to support an absolutely insane launch cadence like that. Still, some people argue, if Starship is fully reusable, what's the point of mass producing it at this scale? It's a fair question, and SpaceX does have a clear reason. First, economics. Elon Musk wants to drive Starship's cost down, but that cost reduction comes primarily from production scale, not from pushing reuse to the absolute limit. Here's the key point. Most of the cost savings from reusability are already harvested within the first 10 to 20 flights. During that phase, the vehicle's build cost gets amortized, and the marginal cost per launch drops sharply, from thousands of dollars per kilogram down to just a few $100s per kilogram. Beyond that threshold, you hit a cost floor. Fixed expenses like propellant, operations labor, inspections, and refurbishment dominate, and those costs don't shrink much, no matter how many more times the vehicle flies. So extending a Starship's life from 20 flights to 40, or even 100 flights, only delivers marginal improvements in overall cost per kilogram. Most of the economic benefit is already locked in early. To push optimization further and drive costs even lower, SpaceX would have to apply Wright's law to Starship production. Under this law, unit cost falls exponentially as cumulative production increases. If both gigabays are online and capable of producing around 1,000 vehicles per year, the estimated manufacturing cost for a full stack, Starship plus Super Heavy, would be roughly $26 million. But once SpaceX scales to 10,000 ships per year, essentially reaching full industrialization, everything changes. Manufacturing costs could drop sharply to around $12.2 million per full stack, driven by true mass production, stainless steel structures that scale easily, high levels of automation, and a massive Raptor engine supply chain. Up to this point, we've only been talking about Wright's law on the manufacturing side. But there's one massive factor that can't be ignored. Starship is reusable. To really make reusability work, SpaceX wouldn't fly Starship and Super Heavy the same way. The booster is built to take more punishment and fly far more often, so it makes sense that one Super Heavy would support multiple ships. In simple terms, about 40% of the build cost sits in the ship itself, and roughly 60% in the booster. Right now, it's basically one ship per booster, but as production scales up, that changes fast. At around 1,000 vehicles a year, one booster could serve 3 Starships, and at 10,000 a year, that number could climb to 5. The more times that booster flies, the more the hardware costs get spread out, and the cheaper each launch becomes. Then you get to the recurring costs per launch, operations, fuel, and refurbishment. And this is where cadence really changes everything. Today, those costs are still high, around $10 million per flight, simply because Starship is still being operated like a campaign. Low launch frequency, lots of people involved, manual inspections everywhere, and very little standardization. But at scale, that entire mindset disappears. The infrastructure is already paid for. Fuel starts getting produced on site, exactly why SpaceX is building an air separation unit right near Starbase. And instead of special launch campaigns, Starship turns into a continuous operation, more like a factory than a traditional rocket program. As that happens, operating and fuel costs drop sharply, and refurbishment changes even more dramatically. Instead of tearing vehicles apart after every flight, the system shifts toward automated checks and exception-based maintenance. You only fix what actually needs fixing. Once you reach thousands of launches per year, refurbishment stops being a major cost driver altogether. When you combine all of that, mass production, aggressive reuse, and non-stop flight cadence, the numbers start to look almost unreal. At around 1,000 launches per year, the cost to reach low Earth orbit drops to about $1 per kilogram. Push that system to 10,000 launches per year, and you're suddenly talking about just a few cents per kilogram. And that's the key idea here. Starship isn't trying to become cheap by making one vehicle last forever. It becomes cheap by flying constantly and being replaced efficiently. At that point, it stops behaving like a rocket and starts behaving like logistics infrastructure, where the real cost driver isn't how long a vehicle survives, but how efficiently SpaceX can build, reuse, and operate the next one. And this is where things stop being just cheap and start becoming a serious competitive weapon. Mass production at this scale creates an entirely new cost baseline, one that competitors simply can't follow. Even right now, Falcon 9 launches for around $50 to $62 million per flight, and that alone was enough for SpaceX to steal huge portions of the market from traditional players like ULA or Boeing, where launches often cost hundreds of millions. Now, imagine Starship, fully optimized for reuse and built like an industrial product. Suddenly, a launch might cost just $1 or $2 million, while carrying 100, maybe even 150 tons to low Earth orbit in a single shot. At that point, the cost barrier to space basically collapses. SpaceX wouldn't just be cheaper than everyone else. It could realistically dominate commercial, military, and scientific launch almost across the board, creating an economic gap that competitors would struggle to close for an entire decade. And Starship doesn't exist in a vacuum. It's a core piece of Elon Musk's broader tech ecosystem. With a massive Starship fleet, SpaceX could deploy millions of next-generation Starlink 5-3 satellites, something smaller rockets like Falcon 9 simply can't do efficiently, either in cost or in speed. At the same time, the links to XAI get tighter. Grok can support Starlink operations, while Tesla's AI software and chips could end up inside Optimus robots, running Starship factories, or even working directly in space. But the most disruptive outcome might be what Starship unlocks next: orbital compute. This idea is already moving from science fiction into something that actually makes economic sense. On Earth, a 1 gigawatt data center can cost $10 to $14 billion once you factor in land, grid connections, and massive water cooling systems. But lifting 10,000 tons of equivalent hardware into orbit would cost only about $100 million if launch prices fall to around $10 per kilogram. At that point, transportation is just about 1% of the total investment, effectively turning space into cheap infrastructure. But for all of those advantages, this approach also creates some very real challenges that SpaceX has to deal with. The first one is the hardest by far: making the jump from experimental prototypes to true industrial mass production. That's a massive leap. Keeping quality consistent across thousands of vehicles, from precision welding on stainless steel tanks to Raptor engine assembly to the thermal protection tile system, demands extreme automation, tight process control, and far less room for human error. When you're operating at this scale, even a small mistake, if repeated, can turn into a wave of failures that slows everything down and drives costs back up. There's also a very practical problem people don't talk about enough. Where do you put all these ships? Thousands of super heavy boosters and starships need somewhere to sit, waiting for launch, waiting for refurbishment, or waiting to be stacked. Each full Starship vehicle is enormous and takes up a huge footprint. At something like 10,000 vehicles per year, SpaceX could easily need tens of hectares of concrete just for storage, servicing, and staging. China has never given up on its ambition to surpass the United States in space. For more than 25 years, the International Space Station stood as the symbol of American leadership in orbit, a project the U.S. spearheaded, shaping the rules and setting the tempo for human spaceflight. But China didn't wait for an invitation. Instead, they built their own path. In just a few years, Tiangong went from blueprint to a fully operational space station orbiting above Earth as a clear declaration of independence. And now, that same determination is shifting toward the moon. On our side, we have Starship HLS, NASA's SLS and Orion, On their side, China is developing the Mengzhou spacecraft and the Long March 10 rocket as the backbone of its own crewed lunar architecture. And now, that architecture is no longer just on paper. On February 11, 2026, China put a key piece of it to the test with a high-profile launch from the Wenchang Space Launch Site on Hainan Island, a coastal complex purpose-built for future human lunar missions. The vehicle was the Long March 10A, a two-stage single-core configuration of the broader Long March 10 family that's being developed to carry Chinese astronauts to the moon before 2030. If you want a simple comparison, think of it as China's answer to Falcon Heavy, except this time flying with a single core instead of three. The rocket stands about 67 meters tall with a 5-meter diameter core. Its first stage is powered by 7 YF-100K engines, burning kerosene and liquid oxygen, delivering enormous thrust at liftoff. And notably, it's designed with partial reusability in mind. The first stage is intended to perform a controlled descent and splashdown recovery at sea. Sitting on top was a test article of the next-generation Mengzhou spacecraft. This vehicle is gradually set to replace Shenzhou, which has been ferrying astronauts to Tiangong for years. But Mengzhou isn't just a station taxi. It's designed for deep space missions, including carrying crews into lunar orbit. It features a reusable re-entry capsule and a high-performance launch escape system built to handle the higher energies of lunar missions. And those technologies weren't just theoretical. They were put on full display during this launch. The mission lifted off at 3 a.m. UTC, and the objective was not to reach orbit. Instead, this was an unusually bold integrated test. The rocket roared off the pad and accelerated, rapidly reaching supersonic speed within seconds. Then, right at max Q, the escape system activated. Solid motors on Mengzhou's launch escape tower ignited, pulling the return capsule cleanly away from the rocket and pushing it safely out of the danger zone. The concept is very similar to the emergency escape system used on NASA's Orion. After separation, the Mengzhou capsule followed a short suborbital trajectory before descending under parachutes. Airbags deployed just before splashdown, allowing it to land gently in a pre-designated recovery zone at sea. Recovery teams reached the capsule in under 90 minutes. At the same time, the first stage did not simply fall away. Using grid fins and engine control for guidance, the booster executed a controlled descent profile and ultimately performed a soft splashdown near Hainan. Visually, the footage looks strikingly similar to recent SpaceX Super Heavy landing tests, although the Long March 10A did not appear as refined or as powerful in presentation. Even so, this marked the first time China successfully carried out a controlled first-stage recovery during a real integrated flight test. The mission was declared a near-complete success with no major anomalies reported. More importantly, it validated astronaut safety systems at the most critical phase of flight and demonstrated that Long March 10A's reusability technology is progressing in a credible direction. The comparison to Falcon 9 is inevitable, though the scale, maturity, and operational context remain very different. As Elon Musk said, they have added aspects of Starship, such as use of stainless steel and methalox, to a Falcon 9 architecture, which would enable it to beat Falcon 9. Several international analysts describe the event as an extraordinary test, because it is rare for any space program to bundle so many high-risk mission-critical objectives into a single launch attempt. But the core question remains, are these impressive advances enough to threaten America's lead in the race back to the moon? The blunt answer is no. Not yet, and the gap is still very real. If we step back and look at proven deep space performance not near Earth test flights, the difference becomes clear. NASA completed Artemis 1 in 2022. Orion traveled more than 1.4 million miles looped around the far side of the moon, endured the extreme heat of lunar return re-entry velocities, and splashed down safely in the Pacific. That was a full deep space mission profile. Real translunar injection, real high-energy re-entry. Years of data now analyzed and feeding directly into Artemis 2. By contrast, Mengzhou has so far completed a max-Q abort test and a controlled parachute and airbag splashdown. That is an important safety milestone. It proves the escape system works under peak aerodynamic stress, but it is still an early-stage demonstration. It has not yet operated in cislunar space, nor has it experienced true lunar return conditions. When it comes to launch vehicles, the separation is even more pronounced. SLS has already flown once on a lunar trajectory, And as of February 2026, it is stacked and preparing for Artemis 2, the first crewed mission to fly astronauts around the moon in more than half a century. Yes, SLS is widely criticized for its cost and slow cadence. But from a systems engineering standpoint, it is a flight-proven heavy-lift rocket that has completed full-duration green runs, stage qualifications, and an actual lunar mission. Long March 10, on the other hand, is still in its developmental phase. The recent test used a single-core prototype, flying a low-altitude profile to validate early ascent abort capability and controlled recovery. That is conceptually similar to the very early booster recovery tests SpaceX conducted more than a decade ago. The full 3-core heavy-lift configuration, the one capable of sending crews toward lunar orbit, has not yet flown. The first orbital mission of Mengzhou may come in late 2026 or 2027. The debut of the fully capable Lunar-class Long March 10 configuration is likely no earlier than 2027. To be clear, China is moving quickly. The engineering learning curve is steep, and they are absorbing lessons efficiently from an Orion-like launch escape architecture to booster recovery techniques that echo SpaceX's approach. But operational deep space experience, end-to-end lunar mission validation, and a system that has already flown beyond Earth orbit still belong to the United States. The gap is not permanent, it is not insurmountable, but at this moment it remains unmistakable. Beyond SLS and Orion, the United States also has something China simply does not: Starship HLS. And this is where the strategic divergence becomes unmistakable. China's lunar lander, known as Lanyu, is modern and carefully engineered, but conceptually, it still follows a classic architecture rooted in the Apollo era. According to disclosures from the China Manned Space Agency, Lanyu consists of two clearly separated elements: a descent module that houses the crew cabin, and a propulsion module that carries most of the fuel and engines needed to break from lunar orbit and control the landing. Structurally, this mirrors the Apollo lunar module approach, separating landing and ascent functions, though updated to carry 2 taikonauts and a roughly 200-kilogram rover, capable of transporting 2 astronauts up to about 10 kilometers across the lunar surface. Lanyu also does not depart Earth together with Mengzhou. China's strategy relies on dual launches. One Long March 10 sends Lanyu into lunar orbit first, where it waits. A second Long March 10 then launches Mengzhou with the crew. The 2 vehicles rendezvous and dock in lunar orbit, and only then do the astronauts transfer into Lanyu for descent. From a systems engineering perspective, this approach reduces near-term development risk. It distributes mass across multiple launches, avoids the need to field an ultra-heavy single-launch architecture immediately, and builds upon China's extensive robotic experience from the Chang'e program. But when you place Lanyu next to Starship HLS, the contrast becomes dramatic. Starship HLS is not a traditional compact lander. It is a modified version of Starship itself, a fully integrated large-volume spacecraft, designed not only for the Moon, but ultimately for Mars. Instead of separating descent and ascent modules, Starship HLS lands the entire vehicle on the lunar surface. The difference in scale is staggering. Starship HLS is expected to deliver on the order of 100 metric tons to the lunar surface in certain configurations, compared to Lanyu's estimated fully fueled mass of roughly 26 tons. That translates into vastly greater cargo capacity, not just 2 astronauts and a small rover, but potentially large surface habitats, heavy scientific equipment, larger pressurized rovers, power systems, and significant logistical reserves to support extended stays. In other words, Lanyu is optimized for short-duration sorties. Starship HLS is designed with infrastructure in mind. Equally important is reusability. Starship HLS is intended to be fully reusable. Its lands can be refueled in lunar orbit by tanker Starships, and then returns without discarding stages. NASA selected it for Artemis 3, not only because it can land astronauts, but because it offers long-term scalability. The architecture can evolve from brief polar missions to sustained presence and eventually to a permanent base camp model. By contrast, Lanyu follows a more traditional round-trip paradigm: land, conduct a short surface mission, ascend, and depart. It is a capable design, but it does not yet embody the same level of expansion potential. Of course, Starship HLS remains under intense development pressure. Orbital flight tests, in-space refueling demonstrations, and lunar transfer validation are still ongoing challenges. Artemis 3 has already slipped to 2028 or later. The program carries real technical risk. But that ambition is precisely the point. The scale, the full reusability, and the architectural flexibility of Starship HLS represent not an incremental improvement over Apollo-style landers, but a generational leap. And let's not forget something important. The United States already won the moon race once more than 50 years ago. This isn't unfamiliar territory. America has done this before. And in this century, with NASA, SpaceX Blue Origin, and an entire commercial ecosystem pushing forward, the industrial base is broader and more dynamic than ever. So the real question is not whether the US has the capability. It's whether it can execute fast enough. Do you believe the United States can beat China to the moon a second time? If you do, drop a 1 in the comments. Let's see where everyone stands. The real winner on the moon won't be the one who plants the next flag. It'll be the one who learns how to use what's already there. That means mastering in situ resource utilization, or ISRU. In simple terms, turning lunar resources into something useful. Water ice locked in the shadows near the South Pole can be split into oxygen for breathing, hydrogen for fuel, and drinking water for crews. That same water can be